This video we are going to discuss the 14 group elements. It's also called carbon group, carbon family. Yes, this is the second group in the P block. Okay, so what are the elements which are coming under this 14th group? If you look into the elements, carbon, silicon, germanium, tin, lead. And recently they introduced one more new element in the NCERT book also, that is FL. You usually fluorine. What is the symbol? F. Okay, this is FL, ferrovium. Okay, it is also radioactive element. And whose atomic number is 114. Why? Because they are 113. So this is 114, and whose atomic mass is 289. Okay, so this is about the atomic mass and atomic number. Okay, come to the point. Carbon, silicon, germanium, tin and lead, these are the main elements. This is the radioactive element, no need to discuss. The first two elements are what? Non-metals. The first two elements are non-metals. Next, the next two elements, germanium is metalloid, and tin and lead, these two are what? Metals. That means when you go from top to bottom, so when you go from top to bottom, what happens? The non-metallic nature decreases, and the metallic nature increases. Okay, so this is about the general elements present in this. And what is the general electronic configuration of these elements? The general electronic configuration is ns2np2. So in the valence shell total, how many electrons are there? 4 valence electrons. That is why we are calling this group as a fourth A group. So the common oxidation states, they exhibits is +2 and +4. These are the two oxidation states the fourth A group elements shows. Okay, so this is the general introduction. Let us restart the periodic properties. Under the periodic properties, the first one is what? Atomic size. So what happens in the atomic size in the group when you go from top to bottom? Okay, so if you check the atomic sizes in the group, when you go from top to bottom, the atomic size increases because of increase in the number of shells, with an exception. So what is the atomic size? Increases from top to bottom with an exception. What is that exception? That is what? Carbon, silicon, germanium, tin and lead. So there was no exception. Carbon, silicon, germanium, tin and lead. So this is about the atomic sizes. So increases regular order only. There was no exceptional cases in case of atomic sizes. Then move to the second property, that is what? Ionization enthalpies. So in case of ionization enthalpy, if you check the ionization enthalpy, so as we know, ionization enthalpy and the size, they both are inversely proportional. So if the size increases, what happens? Ionization enthalpy decreases. So it decreases from top to bottom with one exception. Here there was one exception. In case of ionization energy, there was an exception. What is that? So from carbon, so decreases, right? Carbon having more, carbon, silicon, germanium, tin, but lead is exceptionally having more ionization energy than tin, because lead having what? There was a lanthanoid contraction. Because of lanthanoid contraction, lead is exceptionally having high ionization energy than tin. Okay, clear? Next, third, electronegativities. The electronegativities will not show the regular trend. There was an irregular order. electronegativities of the carbon family are irregular, because they won't follow a regular order. What is that? So carbon, and usually electronegativity decreases down the group, so that is why carbon is exceptionally having high electronegativity in this group, and thereafter remaining elements, silicon, germanium, tin. Okay, so this is exceptionally smaller, tin, lead. Okay, so this is what almost silicon, germanium, tin, lead, these all elements are almost having the equal electronegativities. Okay, slightly 0.1 and 0.2 is greater for lead, but almost these four elements are having almost equal electronegativities, but only carbon is having high electronegativity because of small size and because of its non-metallic nature. Okay, so this is what the electronegativity is. Next, move to the fourth property. That is what? Density. Density. So what happens? What is the regular trend of density? So as we know, in any group, when going down the group, the density increases. So it is also the density is following regular order only. That is what increases from top to bottom. There was no exceptional cases in case of density. Next one, coming to the melting point. When you come from carbon to, actually the melting point decreases down the group, but with one exception. So it decreases from top to bottom with an exception. What is that exception? Let us see. Carbon less than decreases. Silicon, germanium, tin, but lead is exceptionally having more melting point. Lead is exceptionally having more melting point than tin. So this is an exceptional case. So almost we can say it decreases by going down the road. Next one, coming to the boiling point. Boiling point, there was no what exceptional cases. It is following the regular order only. Regular order only. That is, it is decreasing from top to bottom. There was no exceptional cases. Okay, that is what carbon, silicon, germanium, tin, and lead. Next one, catenation. What is mean by the catenation? Catenation is nothing but the ability of a species to make longer chains. Okay, that is what we call as a catenation power. Because this catenation is because of what? High strength of CC bond. Okay, the catenation ability is more for what? Carbon. So carbon strength is more than Si than remaining bond. That is why catenation power is more for carbon. Okay, and this catenation power, exceptionally carbon is having more catenation power than silicon, than germanium, than tin. But remember that, so almost they both are having same, but remember that lead doesn't show the catenation behavior. Last 2019 JEE question. Okay, so which among the following do not exhibit the catenation? Okay, all 14 group elements will show the catenation behavior except lead. Okay, next, after the catenation, let us move to the oxidation states. Oxidation states. So coming to the oxidation states, as we know, when you check these oxidation states, let us check the oxidation states. Carbon, silicon, germanium, tin, and lead. So the above all will show the +4 oxidation state, and it is showing the +2 oxidation state. That means by going down, what happens? The stability of +2 oxidation state, +2 oxidation state stability increases, and the +4 oxidation state stability decreases. What is the reason? Because of, already we discussed, because of inert pair effect. Because of inert pair effect, the stability of lower oxidation state is increasing, and the stability of higher oxidation state decreasing by going from top to bottom. And because of that reason only, when you compare tin and lead, so Sn+2 and Sn+4, Pb+2 and Pb+4. Now tell me which is a strong reducing agent and which is a strong oxidizing agent. Let us see. As we know, when we compare the Sn+2 and Sn+4, which is a more stable oxidation, +4 is oxidation more stable. So stability is Sn+4 is more. That means if we take Sn+2 is happily what releases 2 electrons, happily undergoes oxidation, and it is acting as a strong reducing agent. Sn plus 2 act as a strong reducing agent. Coming to Pb plus 2 and Pb plus 4, now tell me which is a stable oxidation state of lead? Pb plus 2 is a stable oxidation state. So if it is a plus 4 oxidation state, it happily gains 2 more electrons. That means it is happily undergo reduction and acting as what? Oxidizing agent. So Pb plus 4 is acting as a strong oxidizing agent, whereas Sn plus 2 act as what? Strong reducing agent. So here one more question also we can answer. So Pb I4 and Pb I2. Okay, which is a stable compound of lead? So what is that? Pb I2 is a stable compound. Pb I4 do not exist because of what? Pb plus 4. Pb will always be exist in the form of plus 2 form only. So it will not exist. So this is about the oxidation states of 14 group elements. Let us move to the chemical properties. Chemical properties of these 14 group elements. In the chemical properties, the first one is action with air. Action with air. So action with air means what? Whenever in the air active components are what? Oxygen and nitrogen. The nitrogen will not react most of the cases. So when these elements on reaction with oxygen present in the air and they forms what? EO type or EO2 type or both, they can form. Okay, E means what? The 14th group element. When these elements are on reaction with air, oxygen present in the air, they forms EO type or EO2 type or both. So let us take few examples. That is the carbon. If you take, what are the oxides which are formed by the carbon? CO2, and the carbon exceptionally forming one more oxide also. What is that? Suboxide, C3O2. Suppose if you take silicon, if you take silicon SiO2, but SiO is very rare cases, very high temperature. So we can say we can remove this SiO, no problem. Okay. Next one, germanium. If you take germanium, can exist as GO2 and GO4. Next, SN also SNO2 and SNO4, and lead PbO and PbO2. Okay, now tell me, out of these all oxides, which are acidic oxides? Suppose you just take this one. In the carbon, these are the main: carbon monoxide and carbon dioxide. As we know, carbon monoxide is what? Neutral in nature. As we know this, it is a neutral. Carbon monoxide is neutral. Carbon dioxide is what? Acidic. Carbon dioxide is acidic. Next, silicon dioxide is also acidic. Okay, remaining oxides of germanium, tin and lead. Remaining all oxides of germanium, tin and lead, all are what? Amphoteric. Okay, remaining all oxides are what? Amphoteric in nature. And when you compare the two oxides, okay, which is more acidic, how can you decide by comparing their oxidation state? For example, they have given SnO2 and SnO and SnO and SnO2. O4 not possible. SnO and SnO2. PbO, Pb2. That's two PbO. Okay, now SnO2 and SnO. So in this case, which is more acidic? Always remember that when you compare the oxides of two compounds, same element, the compound where the element is in the highest oxidation state is always been more acidic. So here Sn is in what? +4 oxidation state, and this is what? +2. So definitely SnO2 is more acidic than SnO. Okay, like this we can compare. So this is about the action with air. Next, let us move to the next one. Action with water. Action with water. One thing, carbon, silicon, germanium. Okay, the first three elements will not dissolve, will not react with water. First three elements, carbon, silicon, germanium, they will not react with water. Next, what about the lead? Lead is reacting with water, but because of the formation of the protective layer, that is what PbO, as like aluminium, the lead also forming a protective layer on its surface, and that protective layer stops further reaction. That is why lead also we can say that it's almost unreactive after some time. Only the tin can react with the hot water vapor, okay, and they forms SNO and liberates what? Hydrogen. Okay, so this is the reaction of 14 group elements with water. Next one, reaction with halogens. Reaction with halogens. In case of halogens, when these elements reacts with the halogens, they forms EX4 type of halides. They form EX4 type of halides. In this EX4 type, and one more thing, all elements except carbon will not react with the halogen and they form halide. That's the point you should remember. Except carbon, remaining all 14 group elements react with the halogen and they form the corresponding EX4. Okay, tetrahalides. And next one. And what about the acidic nature of these halides? By going down the group, okay, what happened? Acidic nature decreases. Okay, and one more thing. Ionic nature increases. Ionic nature increases, covalent character decreases by going down the group. And when these halides, for example, EX4 on hydrolysis, what will come? EOH4 will come, obviously, because all halogens have been replaced with OH minus and we get tetrahydroxides. For example, SiCl4, this on hydrolysis, what will come? SiOH4, silicic acid. Okay, CCl4 on reaction with water at 500 kelvins, 500 degrees. Remember that CCl4 on reaction with water vapor at 500 degrees will get a poisonous gas, that is what? COCl2, phosgene will come. Phosgene, CCl4 on hydrolysis, what we are getting? COCl2 will come. Okay, so this is about the reaction with the halogens, and these are the chemical properties of 14th group elements. And after the chemical properties, okay, let us discuss some compounds of 4th A group elements. So first of all, compounds of carbon, let us discuss compounds of carbon. Okay, now as we know, the important compounds of carbon means carbon monoxide, carbon dioxide. If you take the carbon monoxide and one more thing, carbides, three compounds of carbon we are going to discuss. The first one, carbon monoxide. You just take the carbon monoxide. As we know, the preparation method of carbon monoxide, if you take, so when the carbon on oxidation, okay, with a limited supply of oxygen, limited supply of oxygen to the carbon, we are getting carbon monoxide. Suppose if you send the oxygen in excess amounts, then we will get carbon dioxide. That's it. And one more method, you just take HCOOH, formic acid, you know, right? Formic acid. To this HCOOH, if you add a dehydrating agent, that is what? H2SO4, concentrated H2SO4, it removes OH and hydrogen in the form of H2O, and remaining is what? CO. So this is one more method of preparation of carbon monoxide. And here you should remember a point that CO is what? Neutral gas. It is a neutral gas. And one more thing, it is having more affinity. It is having more affinity towards iron present in hemoglobin. How many times it is having more affinity? Approximately 300 times more affinity towards hemoglobin than oxygen. So because of having more affinity than oxygen, the CO is more dissolved in hemoglobin and they form carboxyhemoglobin. With this, the percentage of oxygen levels in the blood will decreases. That is why there was a one precaution. If you burn the coal, in a closed room, what happens? It will, in a limited supply of CO gas will produce. If the CO, if you inhale, okay, that CO having more affinity towards hemoglobin, so it will hemoglobin converted into carboxyhemoglobin. So slowly that person, suppose if you are in that closed room, okay, that person may unconscious after some time, suffocated, and after some time he may die. So that is why you should be very careful while you are burning the coal. You should open all windows and everything. Okay, that is one of the precaution. Okay, anyhow, so this is about the carbon monoxide properties. Let us begin. CO having a excess electron in the form of lone pairs. That is why it is acting as a ligand. We can use them as a ligand. So this is about the carbon monoxide. Next one, carbon dioxide. If you take the carbon dioxide, first already we discussed carbon, when we supply the excess amount of oxygen, we will get what? CO2 gas. And this is a gas which is affecting or which is causing the greenhouse effect, and also photosynthesis effect and greenhouse effect, all are belongs to what? CO2 only. And how can we prepare the CO2? It can be released by what? CaCO3 on decomposition, on heating, we will get CaO and CO2. There is one more. Else to this CaCO3, if you add acid like HCl, also we will get a CaCl2 plus H2O plus CO2. So like this, there was so many ways for the releasing the combustion of fossil fuels. Okay, these are the ways, and combustion of hydrocarbons. Fossil fuels are nothing but hydrocarbons. This all releases what? Carbon dioxide into the environment. Okay, and the carbon dioxide is what? Acidic in nature. What is hybridization? sp hybridization. Carbon dioxide is what? sp. Why? Because C double bond O, double bond O. This is what the structure of carbon dioxide. Of course, we can draw two more resonating structures also. O plus, this is one, and one more thing is, but this resonating structure and this resonating structure, they are less contributing to the structure of CO2, and this is more contributing. That is why the CO2 structure is this one. In this CO2 structure, the carbon is involving in 2 sigma 2 pi bonds. That is why what is the hybridization of this one? This is sp hybridized. Sp hybridized. Okay, that is what? Carbides. Carbides. So in this carbides, the carbides we are dividing into 3 types. Those are, I'm just giving the names: ionic carbides, covalent carbides, and the third one, interstitial carbides. So 3 types of carbides, and they are ionic, here they are covalent, and they are what? Interstitial. That is why they are based upon that we are classified. And these ionic carbides, again we are further dividing into 3 types. That is methanites, next one acetylites, and the third one allylites. Yes, what is the formula of methanites? Methanites means they are C minus 4. Methanites where the carbon having minus 4 charge, C minus 4. Acetylites means C2 minus 2. C2 minus 2. That is our general formula of acetylites. Next, allylites means C3 minus 4. Okay, allylites formula C3 minus 4. Okay, how can you say? This is the methanites means, just write this one, CH4, you remove 4 hydrogens. If you remove the 4 hydrogens, what is the remaining? C minus 4. It's coming from where? Methane. That is why it's a methanite. Next, you take acetylene, CH triple bond CH, no? Acetylene means C2H2, and you remove these 2 hydrogens. If you remove the 2 hydrogens, what is the remaining? C2 minus 2. And if you take the allenes general form, what is the structure of allenes? CH2 double bond C double bond CH2. That is the structure of allenes. So the molecular formula is C3H4, and if you remove the 4 hydrogens, what is the remaining? C3 minus 4. That is why we call them as allylites. Okay, so the compounds which are formed by this carbon, that is C minus 4, C2 minus 2, and C3 minus 4. All we call them as methanides, acetylides and allylides respectively. Next, covalent. Covalent means here they are covalent in nature. So what are the examples for the covalent hydrides? That is beryllium carbide, that is Be2C. Boron carbide, that is what B4C3. Okay, boron carbide, silicon carbide. So these are the best examples for the covalent. Okay, interstitial means there the carbons are present in the interstitial spaces. Okay, these are the carbides. No? So let us move to the next concept. That is what compounds of silicon. Compounds of silicon. So in the compounds of silicon, the first compound is what? Silica, SiO2, and the second compound is silicones, silicones, and the third one is silicates, silicates. These are the three compounds we are going to discuss now. Silicon, silica is nothing but silica is nothing but SiO2. So if you take the SiO2 structure, if you do the SiO2 structure, SiO, like this, what happened? The total 1, 2, 3, 4, 5, 6, 7, 8. 8-membered ring will form. And in this silica, one point, this is what network-like structure, network-like, case-like structure, where silicon is undergoing sp3 hybridization, and it is what 3D structure, 3-dimensional structure. Okay, and this silica, what is the nature of this one? It is what? Acidic in nature. Acidic nature. Because of its acidic nature, what happened? It can be reactive with bases. So okay, when SiO2 reacts with bases like NaOH, Na2CO3 and MgOH twice. These are the bases, any base, and they forms what? Their corresponding salts. That is what? Na2SiO3, silicates, like this. Their corresponding salts will form. And one more thing, it can also react with the HF, only HF out of all acids. Okay, all acids are not, only HF. Okay, it can react with only HF and they forms SiF4 minus. SiF4, and also if it further reacts with this HF, okay, there was a chances of formation of H2 SiF6 minus. Okay, there was a further reaction, but of course here SiF4 minus it will stop. If you further react with the HF, there was a chance of formation of this one also. And one more point you should remember, that is what? SiF6 minus is possible. It's possible. It can exist. But SiCl6 minus cannot exist. What is the reason? Why? Because in SiF6, the silicon atom is surrounded by 6 fluorine atoms. All fluorine atoms are small in size, so there was no spherical hindrance. But in case of SiCl6, the silicon atom is surrounded by 6 large fluorine atoms. Because of bulkiness, because of larger size, there was a spherical hindrance. That is why SiCl6 doesn't exist, as SiF6 can exist. Okay, and this silica can exist in two forms: crystalline form, okay, and amorphous form. Crystalline form we call it as what? Lignite. The name of the crystalline forms of silica is lignite, tridymite, cristobalite. Whereas amorphous form is kieselguhr. Okay, so this is about the silica. Next, this is insoluble in the water. Next, coming to the silicones. What are silicones? So silicones are nothing but the organosilicon polymers. Organosilicon polymers, we call it as what? Silicones. So on these generally how to prepare the silicones. So when alkyl halides reacts with the silica, okay, we are getting different types of organosilicon compounds. In that what? R2SiCl2 or X2, Okay, dialkyl silyl halide or trialkyl silyl halide or tetraalkyl silane. Tetraalkyl silane. So like these different types of or else one more thing, RSIX3 also will form, monoalkyl silyl halide. Like these different types of silyl halides will come. These on hydrolysis. Now these halogens have been replaced by the OHs, and we will get R2SiOH2 will come. Okay, now these are the monomers. By using this monomer, they undergo polymerize. So how they polymerize? Let us see. So Si R OH OH. So dialkyl silyl. Similarly, you take one more OH Si OH R. Now what happened? They undergo polymerization and they undergo dehydration, and we will get OH SiO SiOH R. Like this, what happened? They undergo, this is what dimerization. Like this, many silicon units are polymerized and we get polymer. Okay, so this is what we call it as polymerization of silicons. Now, what is the use of this? Suppose if you wanted to cap the polymerization. Capping means what? Terminate the polymerization. So then what we will do? We will polymerize with trialkyl silyl halide. So trialkyl silyl halide R3SiX is used to terminate polymerization. Suppose if you use monoalkyl silyl halide RSiX3, okay, so we are using this for the preparation of sheet silicates. Okay, three-dimensional silicons we can prepare by using this. Okay, next one. In this silicon, the alkyl groups are what? Hydrophobic, water repellents. So because of this hydrophobic presence of these alkyl groups, okay, these silicons are what? Water repellents, and they are having high dielectric constant, okay, and having electrical insulation, and they are having high resistance towards chemicals or oxidizing agents like this. Okay, so these are some uses of silicones. So after the silicones, let us move to the third compound, that is what? Silicates. Yes, silicates again of different types are there. I am just giving you the general structure and how many of oxygens they are sharing. Okay. Yes, the first one, orthosilicates. Orthosilicates means here only one unit is there, so there was no sharing of oxygens. No sharing of oxygen atoms. The general formula is SiO4 minus 4. So for orthosilicate units, what is the general formula? SiO4 minus 4. So if you take the SiO4 minus 4, SiO. Okay, if you see from the, suppose if you see the silicate emitter, so this is silicon, oxygen. If you see from the top, okay, we can able to see only the front oxygen. Silicon we cannot observe. So that silicon I am representing with a dot, and this oxygen as like this. Okay, and the remaining as what? So it is appearing like what? It is appearing like trigonal planar. So each silicate unit we are representing as trigonal planar shape. Okay, so this is the what? Orthosilicate. Next one, pyrosilicate. So what is the general formula of pyrosilicate? That is what? Si2O7 minus 6. Si2O7 minus 6. And each silicate unit is sharing one oxygen atom. Suppose if they share one oxygen atom, then pyrosilicates will come. Let us see. See, suppose you take two silicate units, Si, O minus, O minus, O minus. It is sharing one oxygen. Once it is sharing the oxygen, there was no negative charge on it. Si, O minus, O minus, O minus. Now tell me, so this is what silicate unit. How many silicon atoms are there? Two silicons. Okay, and how many of oxygens they are sharing? One oxygen. So two silicate units are sharing one oxygen. Each silicate unit is sharing by at one corner, and they both are shared by one. So what is the how many of oxygens are there? 1, 2, 3, 4, 5, 6, 7. 7 oxygen. That is by Si2O7. What is the total negative charge? Minus 3, minus 6. It is not having any charge. That is why Si2O7 minus 6. So there are two types of silicates, and one more type, that is what? Cyclic silicates. In the cyclic silicates, chain silicates we will discuss. Chain silicates. Chain silicates again of linear chain silicates, linear chain and cyclic chain silicates. Linear chain and cyclic chain silicates. If you take the linear chain silicates, so for these both linear chain silicates and cyclic chain silicates, the formula of the silicate is same. That is what? SiO3 minus 2 n times. SiO3 minus 2 n times. So let us see. So in case of in both linear and cyclic chain silicates, okay, they are sharing two oxygen atoms. Okay, each silicate unit is sharing how many of oxygen atoms? Two oxygen atoms. Two corners they are sharing. Let us see how. So I am taking like this and I am drawing like this one, triangle. So that means see, this is one silicate, this is another silicate, this is another silicate. Now if you take this central silicate is sharing how many of corner oxygen? Two corners. Okay, if each silicate is sharing two corners, then that silicate we call it as what? Linear, and this is a linear form. That is a linear chain silicate. Next, cyclic chain silicate. If you take cyclic, yes, here how many silicates? 1, 2, 3. 3 silicate units are there, and each silicate unit is sharing two corners only. Even this is also sharing two oxygen atoms only. So in both linear chain silicates and cyclic chain silicates, what happened? Only they are sharing two corners only. So this is the chain silicates. And last one, that is what? 3-dimensional and 2-dimensional. Just remember one point. In 2-dimensional silicates, how many of corners or how many of oxygens are sharing by each silicate? Just remember that is 2.5 oxygens. In 2-dimensional, how many of oxygens are they sharing? 2.5. Next, in 3-dimensional chain silicates, in 2-dimensional, 3 oxygen atoms they are sharing. In 3-dimensional chain silicates, okay, all 4 oxygens are sharing. All 4 oxygens are sharing means, best example, silica. Okay, in silica, as we know, each silica, okay, 4 oxygens are there, and those 4 oxygens, all 4 oxygens are bonded with other silicon atoms. So silica is the best example for what? 3-dimensional silicates. Okay, and in these silicates are those silicates. In some of the silicon units, if this silicon atom is replaced by aluminium, okay, Si plus 4 becomes what? Al plus 3. So the positive charge decreases. Positive charge decreases means what? Negative charge increase. And to neutralize that negative charge, some cations like K plus, Na plus, Mg plus 2 are coming to neutralize that increase in negative charge. They are called what? Zeolites. Okay, zeolites. And those zeolites we are using for what? For cracking the petrol. Okay, for best example, ZSM5. Or for the removal of hardness of the water. Just example, pyrolytic process, zeolitic process, that we are removing the permanent hardness of water. And best example, ZSM5. ZSM5. What is the role of ZSM5 zeolite? It converts alcohol into gasolite. ZSM5 zeolite is converting alcohols into gasolite. So these are the compounds of the 14th group elements. I hope you all of you having some idea, okay, about the 14th group elements. Thank you.